Alright, ccna2 Chapter 4, Routing Concepts. Basically how a router works before we go into other things. Fairly long chapter. Describe the primary functions and features of a router. Connect devices for a small routed network. Using CLI, configure basic settings on a router to route between two directly connected networks. Verify connectivity between two networks that are directly connected to a router. Explain encapsulation and de-encapsulation process used by routers when switching packets between interfaces. Explain the path determination function of a router. Explain routing table entries for directly connected networks. Explain how a router builds a routing table or directly connects networks. Explain how a router builds a routing table using static routes. Explain how a router builds a routing table using a dynamic routing protocol. Alright, so good times here. Static routing and a little bit of dynamic routing. Alright, so network characteristics. Alright, we have topologies, logical and physical. We need reliability, we need speed. Stuff costs money. We need security, we need availability, we need scalability, we need reliability. Routers allow us to have all these things. They allow us to build topologies. They give us the speed to different networks. They scale us to different networks. They give us the ability to go to different networks, so it gives us higher network availability. And they can do ACLs and all kinds of things, so they're secure. Or we can keep our network out, right? Reliability. I don't know, I guess they're reliable, right? Okay, so why do we route, right? So we can connect two networks. And routers route packages. Oh, look at that 1841 ISR. Woo! Hot dog. Anyways, what's going on here? Alright, so it's just showing you a routing table of, if you guys want to do this, can't see this, feel free to pull open Packet Tracer, put a network on one side and a network on the other side, because that's our first lessons of routers. Okay, so routers separate networks by interface. Over here, this black circle is always going to be a different network than this yellow, because this router interface indicates different networks. If you tried to program this, it would, within the same network, it would give you an error. And anything that is directly connected to a router is known with a C, and that's how routers first learn their tables, is directly connected neighbors. Okay, and that's a real fast rundown of what we're going to be talking about. So, what is composing a router? Just like a switch or anything else, a router is a computer. It's used only to route, right? We could build a computer that didn't look like a router and just build stuff so it would route just like we build switches to switch, right? Switch has computer components as well. So what do we have? We have a CPU, an operating system, RAM, ROM, NVRAM, flash, and a hard drive, which flash is kind of the hard drive, so I'm not sure what this other hard drive is. I guess we can put USBs on these, so maybe we can add external hard drives as well if you wanted to look at it that way. But, so what's running in the RAM? Alright, so RAM is volatile memory. You know this from A+, I hope. So, and volatile means when you power it off, it's gone. It's not saved, right? So RAM works exactly like when we run RAM on a computer right now. In the RAM, it's running the OS, right? It's running all the stuff. That's why if we look, the OS is going to take up most of our RAM, and then we have RAM for the other computers. It's our fast access memory. And so in a router, it's the same thing. What does RAM run? The iOS, the operating system, the running iOS, okay? So it's not where it's stored, it's where it's stored while it's running. The running configuration, when we do a show run, we're looking at into RAM, IP routing and ARP tables, the temporary tables that when we restart them, we have to rebuild them. The reason we have to do that is because IP routing and ARP tables are built in the RAM and the packet buffer. So the packet buffer is when we receive information on one side and we receive too much to forward it on this side. The packet buffer buffers it. It waits to be sent. So that's a packet buffer. Then we have the ROM. The ROM is non-volatile, meaning it's saved. And you guys have probably heard of ROM before. And hopefully you've heard of Ramen. Ramen is the most basic operating system we have on one of these devices, and that's why they say limited iOS, this Ramen thing. Basic diagnostic software like the Post and that kind of thing. Boot up instructions. Where are we going to load the operating system from? Then we have the NVRAM, right? And so the NVRAM is non-volatile RAM, and it's kind of special. It's like this. It's just NVRAM, and all it saves is the configuration file, and it's built into this thing. Then we have the flash, and the flash is like our hard drive. The flash is our hard drive, and it's non-volatile, and it's where the iOS is saved before it's running. So the saved iOS, if we have one, is saved in the hard drive, just like in Windows. Windows is saved in our hard drive, and then it's loaded as we boot up. And then other system files, if we're doing other things, they're also going to be saved in flash. Okay, so that's how those things work. What do we have on a router? Well, we've talked about this before. An auxiliary port. Remember, that's for emergency situations where we're far away. A modem bank is going to dial into this router and save our lives if we crash something. Then we have a console RJ445. Remember, the console cable goes serial to RJ45, Cisco proprietary, and allows us to initially configure this device, or in an emergency case where we can get to the device, that's how we're going to get in. And those are our two out-of-band. Auxiliary and console or out-of-band management. Then on the newer ones we have a console USB Mini B that we can use, like I guess we use a cell phone or something. I don't know why, I guess it's just a smaller cable. USB ports, if we in an emergency situation we could load in a different operating system, or we could save our backups, I guess, to a USB. I have only used them to load in a different operating system. Then we have LAN interfaces, and the LAN interfaces are the ones that this router connects to switches, right? So we have switches over here. Anything that those are switches. I'm sorry that one looks like a triangle, maybe a piece of pizza. And then over here we have this lightning bolt cable known as a serial cable, and that just virtualizes a WAN interface, which it goes into these modules here, right? We have these, oh no, those are flash spots, sorry. So we only have one WAN module here. Oh no, they're here. We have double wide down here. Never mind, we have more. And then we have flash card backups or whatever, expansions, redundancy of some sort. Okay, so that's the outside of the router. And so the primary job of a router is to direct packets to their proper destination, to connect routers. What are routers routing between? Networks, okay? And if we're directly connected, right, like if this is just one network, they're directly connected, so that router already knows here and here. But we need an actual routing protocol or something, or a static route, because we have a WAN link. Because of that, this router knows about, say we're in R2 right here. So we're in R2. R2 knows about the serial network because it's directly connected to it, and he knows this LAN network. Okay, but the LAN network connected to R1 is not directly connected. So if the router tried to send packets there right now, it could not do that. All right. We have to put in a routing protocol to do that, or a static route, and then it could. And so then the routes are going to route between packets. What else does it say? It's just they do best path selection. Sorry, that took me so long. And then send the traffic along their way. And so this is where routers are what are connecting us to the internet, because the internet's a bunch of networks, and so they're usually our last hop, and they can work as a firewall and all of that jazz. They're great. So routers choose the best path, and so they determine the best path to send the packets and forward packets towards their destination. Why packets, not frames? Remember, switches forward frames. Routers forward packets. They're a layer 3 device, just like a computer. And plus the packet is a layer 3 topology. And so they're looking for a destination. Basically, a router is saying, hey, I'm looking at this packet, and where is the destination address, and if do I know it? Otherwise, send it there if I know it. Otherwise, send it into the bit bucket or the garbage. So, packet forwarding mechanisms. This has to do with how they're forwarding, kind of like how we went over switches. Switches, we had these different forwarding mechanisms. So we process switching. An older packet forwarding mechanism still available in Cisco routers. When packets arrive on an interface, it forwards it to the control panel where the CPU messages the destination address with an entry in its routing table and then determines the exit interface and forwards the packet. It is important to understand that the router does this for every packet, even if the destination is the same stream of packets. This process switching mechanism is very slow and rarely implemented in modern networks. Okay, and this is why you used to do a lot of layer 2 because layer 3 switching was so slow, just like they were talking about. So then we upped it. We have fast switching. This is a common packet forwarding mechanism which uses fast switching cache to store the next hop information. When a packet arrives on an interface, it is forwarded to the control pane where the CPU searches for a match in the fast switching cache. If it's not there, it is process switched and forwarded to the exit interface. The flow information for the packet is also stored in the fast switching cache. If another packet going to the same destination arrives on the interface, the next hop information in the cache is reused without CPU intervention. So once it's routed once, it builds a database of where it's going. Okay, which led to, why Cisco devices are great, Cisco Express Forwarding, CEF. CEF is the most recent and preferred Cisco IOS packet forwarding mechanism. Like fast switching, CFS builds a forwarding information database. Alright, so it's similar, but it uses these two databases. The FIB, and an adjacency table. So it uses a FIB and an adjacency table, whereas like the last one basically just built this FIB. So the table entries are not packet triggered like fast switching, but change triggered, such as when something changes in the network topology. Therefore, when a network has converged, the FIB and adjacency tables contain all information a router would have to consider when forwarding a packet. The FIB contains pre-computed reverse lookups, next hop information for routes, including the interface and layer 2 information. Cisco Express Forwarding is the fastest forwarding mechanism and the preferred choice of Cisco routers. Alright. So, shows you the difference between FIB and between these mechanisms and these graphics. First one, straight CPU. Second, fast switching, some of it's CPU, and the third one, it's built these routes and it's ready to go using a lot less CPU. Alright, so network devices connect to networks and they need to go to the WAN, and that's why we typically, so if we're just connecting to the LAN, connecting people, switches make up the LAN. We could have, everybody could connect to each other through the LAN if they're all in VLAN 1. Now if we had multiple VLANs, we need a router to route between them, but that's for a different day. So anyways, what they're talking about here is home offices versus the branch, right? And so home offices probably have one router that just goes to the internet, something like this, whereas our branch has multiple, some of it's going to the cloud and the internet. If you guys have forgotten, the cloud, this could be like a private or hybrid cloud but rather than the internet, or maybe they're talking about a frame relay cloud. Anyways, it's just a group of networks across a distance with this cloud. Resources have gone rather than the internet, which is public, completely public. This could be all private. Anyway, so we're going on like that, and these routers are going to connect these networks. The routers, as you see, are all the WAN links, whereas on our home router we are getting Ethernet from cable or DSL or whatever we're doing. Alright, so routers are the default gateways, and I know everybody remember the default gateway is how we get out of our network. And so our default gateway is always in the network, and it's usually a router. At some point it becomes a router. Alright, so, and what the default gateway says is, if you're not in my network, I send it to my default gateway. The way out, the exit of the room, okay, if the room is a network. So that's what default gateway is. So the IP address, you know, like our subnet tells us where our network starts and stops. I know you guys remember that perfectly. And then our default gateway says, hey, if you're not in our network, based on our subnet, we send it to the default gateway. Then if the router knows the network, it either forwards it or it doesn't, right? So either traffic gets there or it doesn't. Document networking addressing. When I talk to employers, what they say is the most important thing is people need to do better documentation. And so you want to document the IP addresses of your device, where they connect, what their default gateway is, and what interface they plug into, like on the switch, all this stuff. This is more, I don't know, this doesn't really have as much to do with routing, except that we need good documentation of networks, especially if we're doing static routing, to be able to do static routing properly. So you guys have seen this before, how to statically set IP address and how to not, which hopefully you guys remember. We do something like this, right? We go into that adapter setting, however you get there, which network and sharing, or network and internet, network connections. You either obtain it. This is DHCP, right? This is setting it manually. Alright. So that's that. So then, device LEDs. What do they mean? Well, you probably won't pay attention to them this much, but hey, it's interesting stuff to know. Apparently, one blink plus a pause gives us a 10 meg on this link. You know, 2 blinks and a pause, 100 meg. 3 blinks and a pause means we're getting a gig out of this function. These greens over here tell us if we're consoled in, and actually on newer ones they have a net blink on the auxiliary as well. So, anyways, take a look at that if that interests you. Console access. Once again, console is RJ45 to DB9 or serial, right? And we do this through either TerraTerm or PuTTY or any terminal emulation software. And hopefully you guys remember that. It's what Packet Tracer is doing. Let's see, do I have PuTTY out here? I closed my PuTTY, I think, but hey, we'll fire that back up. Right, so if we're going to console, we go clear over to the right on the PuTTY, we pick our COM port. How do we find our COM port? Well, if we're in Windows 7, we'd have devices and printers and devices over here, so we could say printers and devices. It's not going to help you guys, but the printers and devices will show you hopefully what your USB to serial is doing, or if you're just using a COM, most computers in this day and age only have a COM1, and so you're going to be using COM1. Usually the USBs, each one virtualizes like COM3, COM4, COM5. So depending on what USB you plug into, it's going to virtualize as that COM, and you're going to change that to serial in, right? You take this pretty blue cable, plug the serial in into your serial adapter or into your serial port. You take the other end into your console. You PuTTY in by clicking open here. I don't have anything plugged in, so it's not going to work. But if I did, it would look just like Packet Tracer, kind of like this. And now if you guys don't remember from doing this before, if you don't see anything here at first, the thing with PuTTY or any terminal emulation, especially when you're going in through serial, is hammer enter at least once to see if it's getting any activity, because sometimes that helps you out. It'll just sit there blank until you hit enter because it hasn't had any activity. So make sure you do that. If you're ever having trouble serialing, hammer enter. Alright, so now that was out of band management. Now in band, if we want to tailnet or SSH, hopefully you guys remember that because it was ccna1, and remember that's where we actually go from the IP address. It's known as in-band net. management or in our network management, we could go back to PuTTY and do it, or we could do it from any network device by typing. Let's see, they have it. Well, no, you can type it, but it's either go here, click SSH or Telnet, and then you put your IP addresses in, right? And if you change the port, you want to change the port number. But if we go into the device, we just say SSH or we say Telnet on the device and then the IP address, and it will do the rest for us as long as we have everything set up correctly. So that's another important reason with Telnet and SSH. What makes our life a whole lot easier is by telnetting to the correct devices. Okay, so documentation. It will say, like, you will be so happy. You'll be annoyed as you do it until you have the problem, and then when you have the documentation, it is worth its weight in gold. Okay, so configure basic settings on a router. You guys have done this before. I'm not going to do it. I'm not going to go over it very much. Right? Device name, same as a switch. Host name, and then we name it R1, or the room name in R1 or R2, whatever it is. Secure management access, right? Enable secret. Configure a banner. You guys have seen this. Go through these commands if you want. 4131, right? All the basic commands, and you need to remember them. I believe I showed them to you guys in the last chapter. So same thing. So now our new one. Well, not really new. Hope you did this in ccna1. So, but how do we configure an IP address? Alright, so we're in global configuration or configure terminal. What would we type? Interface gigabit 00 or whatever interface it is. How do we figure out what interfaces we have? We can always go out to privileged exec, right? And we do a show running config. If we do a show running config, it's going to show us everything we have configured. Right? So I pull up one of these routers. It's not going to show anything because I don't have anything programmed, but I could do show run, right? And if I do my spacebar through there, it shows me I have gigabit 00, gigabit 01, and an interface VLAN 1. Now remember, this is an SBI. We do not want to use this right now. This is used for advanced stuff when we use a switching module in a router. It's not covered by CCNA, so we're not going to talk about this, but never program interface VLAN 1 in a router. That's only for switches. At least in this class. And so now it shows us that we have 2 gigabit interfaces and we can do whatever we want. We also notice by default they're shut down. Their speed is set to auto. Their duplex is set to auto and they have no IP address. Okay, so how do we set an IP address? Well, first we do IP address. I'll just do it for you. Alright, so what do? Global config. Configure terminal, right? Interface G00. I could turn this on right now if I wanted to, but the first thing I'm going to do is IP address 192.168.1.0. No, I'm not going to do 1.0 because I'm going to put a /24 on it, and that is called a network address, and that's one of the addresses I can't use. So I do a 192.168.1.1 or any other usable host address in a network to put an IP address on that router. Then I say no shutdown, right? And I turned it on, and so now that thing could connect into a 192.168.1.0 network. This one says 11 and 12, so it's a different network, but it's on, and that's basically all we have to do to configure that interface. Okay, now we set an IP version 6 one. So now we have 2 different options, and hopefully you guys remember that. So I'm still in my interface G00 here. So how do I set an IP version 6 address? I say IP version 6 address. Hard one to remember, right? Then I do a question mark, and I'm sure you guys remember, but on your IP version 6, you have a few more numbers than the IP version 4. Remember, IP version 4, we have 4 octet. In IP version 6, how many do we have? Well, we have 128 bits, and each one of these is worth 16. So we could have 8, but remember we have that double colon that can represent continuous zeros, and so we're going to go like this. We're going to say IP version 6 address, and we're going to say 2001::1, Alright, which means it's just 2001 with a bunch of zeros, and I'm going to give it a /64, and that's how we set an IP address there. Or we could do an FE80, and hopefully you remember FE80 : 1. FE80 is always, this one's a global unicast of 2001. Anything that starts with FE80 is a link local, and to set the link local, we say IP version 6 address again, FE80 : 1, and instead we say space link local, and that sets the link local on that interface. Because when we set IP version 6, hopefully you remember, they can be dual homed, and so we can have several networks on, we can have a link local on an interface and a global unicast on an interface, so we can set multiple IP version 6 addresses on an interface. Okay. Another one that we could set if we want to just have it self-generate is we could do the EUI64, which configures a global unicast IP version 6 address with an interface identifier in the low order 64 bits of the IP version 6 using the EUI64 process, which is basically taking the MAC address, splitting it in half, and putting some E's in the middle of it. So not really used anymore, but yeah, that is, you have link local or the IP version 6 with the multicast. But if you want to build a unique identifier based on the UI64, put the UI64 in there instead of link local. Don't think that's supported by Packet Tracer, so you don't have to worry about it. Alright, so we can configure a loopback interface. This is new to us. A loopback is just a virtual interface that doesn't exist, kind of like an SBI, except more like a physical interface. And so what we would do is we just exit this router, right? And we say interface LO0 for loopback 0. We could do interface LO1. If you guys are doing Packet Tracer and you want to put a whole bunch of networks in, test your knowledge as you build these routing protocols, you could build as many networks as you, well, probably not unless you want like, I don't know, 200 networks, but you could build several networks in one router just by using the loopback. Okay, and the loopback, right, remember on a computer is just 127.0.0.1, test stack with it. With the loopback, this virtual interface, we use it for routing and other things, but or they used to, it's kind of legacy now, but it's just a stable interface, right? Because on a physical interface, we can unplug a cable and that interface goes down. A loopback, as soon as we turn it on, as long as the device is still on, it's gonna be on. So that's what a loopback is. So how do we verify our settings? Well, we have a set of commands. We have show IP interface brief, which I think we talked about on the switches as well, right? So it's just going to show you what you have assigned to your interfaces, if they're up, if their protocol's up, if their line is up, right? So that's just making sure you said no shutdown. But it's just a real easy, short little summary showing IP addresses for each interface. Then we do to show IP route, and this is going to show all IP routes we see. And so in this figure, we see two. We see C's, which stand for connected, and L, which stands for local. And this L is a newer thing. You'll only see this on a newer router. Like our 2911s in class will have this, but our 2800s will not. The connected actually shows you the route. So this is the network it's connected to, alright? So it's saying, hey, G00 is directly connected to here, right? And that's what we're going to see when we look in the routing table. It says C, gives you the network address with the prefix number, is directly connected, and it says G00. And then you'll notice that the local is in that network. And so what the local is the actual, what the interface IP is of this router. So that it will forward it directly to it, right? So you have a /32, which is all ones in our subnet mask, and so this local says this is only me, and so it's basically just putting itself at the highest bits, and we'll figure out why it's doing that as we talk about routing further on in this chapter. This is a fairly long one, so if you're getting bored, maybe you want to break this one into several days. But anyways, back on to our show commands because they're awesome. This would also show the other things that we can see. It would show us up here. We could have static routes represented by an S, RIP by an R. It says BGP. Where are the other ones? The rest of it's omitted. But we have O for OSPF, D for EIGRP. I know that's confusing. And those are our basic ones. We'll talk about them as we go over dynamic routing protocols. Anyways, as we keep going, we have show running config. Okay, I'm not going to go over that one because, well, you guys have used that a whole lot, I hope, because it's my go-to command for troubleshooting. So, show run, what's it going to do? We saw it at the beginning. It's going to show us everything we've programmed. Oh, and look, this is part of the documentation on the interface. Remember, this is a horrible command in that first ccna1 activity where you type description into the link to tell it what network it's going to. So don't forget that. That's part of your documentation, the description command inside of interface. Okay, so verify IP version 6 settings. Basically the same commands, but with IP version 6. Do we have anything new? No, we do not. Okay. We're not. You can filter show commands by using the pipe command. You guys can look through that if you're interested. I've never used it, so I'm not even going to worry about it. It's better to know where everything is on your router, but I guess if you have a huge configuration, it wouldn't be bad to know. Command history, we've talked about this. Here, if you see if you type terminal history size 200, that's how many commands it's going to be. So you could actually limit this command by saying terminal history size 1, right? It would save 1 command. Yeah. And so where would that be good? If you're afraid someone's going to come up to your keyboard and, I don't know, up arrow to something sensitive. If you want to see what it's set at, you can say show history. Same with on a switch. Alright, so router switching functions. And this has to do with, as you can see, encapsulating and de-encapsulating. And we should already know this, right? We know how routers work, okay? I hope. So what happens is we get this whole OSI stack, right? And then it goes into bits across here and it comes into frames. And so the the router starts getting frames and it builds them into packets, right? So de-encapsulates the layer 2 frame header and trailer to expose the layer 3 packet, then examines the destination IP address of the IP packet to find the best path in the routing table. If the router finds the best path to the destination, it encapsulates the layer 3 packet into a new layer 2 frame and forwards it out the same frame. So this brings up our idea on our de-encapsulation. Remember, our layer 3 addresses are the ones that never change. Our layer 2 addresses are going to get ripped off at every router. So at first, we have a source destination here, and it's going as our MAC address. Our IP addresses stay the same, so it's always going to be sending to here. But in this yellow network, first we have MAC of PC1, and then we have the destination MAC of the default gateway, which is R1. And then those are going to get ripped off by that computer, and it's going to put on, then it's going to, if it has that network, it's going to forward it on, and it's going to say the source interface is F01 of R1, and the destination is F02. And remember, these are MAC addresses, or layer 2 addresses that we're talking about. Okay, so it gets to there, and then this router rips it off and replaces the source and the destination, and then finally it gets to this router and it is ripped off. But actually it's not ripped off here. Remember, this is the original packet, so this would be 3 times before it got to its destination, not 4. Not 4 from the original, because this is the original. So the layer 2 changes each time, and we call that a hop, and that's what you're saying within the trace route. That's why if you did a trace route, you're not going to see layer 2 stuff, because it's not ripping those off. It's just traceroute is tracing between networks. Oops. Get rid of that. We've talked about, hopefully we've talked about the AND operation. That's where it says, hey, ANDing is looking at that subnet. Is it in my network or is it somewhere else? And so it's either sending it to the default gateway or just fast switching it within its local LAN, right? So we use that ARP table, and hopefully you remember that ARP table is what a router and a PC use, not a switch. Switch uses a MAC table, it only forwards frames. But any layer 3 device maps a layer 3 to a layer 2 address through the ARP table. That's how it gets. It says, I want to go to this IP address, who has it? If it doesn't have it, does an ARP request, gets it, and then it sends it to that MAC address through that ARP table. Alright, so we're going to see similar things as what I was talking about in these videos. It's basically my drawings of each hop. It's just showing the router ripping off the layer 2, looking at the destination IP. So this is destination IP is basically what the router looks at because it wants to know where to forward it. It already knows it's going to keep the source IP right now until we get a network address translation, and then it changes that. But the most important is destination because it says, hey, destination is where it's going, and that's what the router cares about the most, is where it's going, not where it's been. Anyway, so that happens, and it keeps going, you know, keep getting this stuff ripped off. Anyways, I kind of explained that already, so feel free to look through here after it sends us packets and those frames are sent to the PC. They're rebuilt into the 7 layer. I guarantee you'll have like 15 test questions that are the same as activity 4216, so it wouldn't be a bad idea to do them. They never go away. Alright, so routing decisions. How does a router route to a network? Well, we've talked about directly connected, right? So directly connected is how it knows it because it's its interfaces. So if we have an interface here and an interface here, those are directly connected interfaces. So we know those ones. Then a remote network would be what's not directly connected, something over here. And so to get there, we have to put a static route or do a dynamic route, or there's no route detected and it throws those bits into this bit bucket down here, which is just a garbage can, and that was supposed to be fire, and so they're burning up in the garbage can. But anyways, so on its routing decision, what happens? Packet arrives. Router searches for the routing table for a match. So it's looking at the destination route. It says, hey, do I have a match? And so it says, does the destination IP address match one of the subnets of a directly connected route? It's going to look directly connected first. And we'll find out why as we go on to this best path section. If not, do I have a remote network? If not, is there a gateway of last resort? So remember, a default gateway is how to get out of a network. And then the router actually has what's called a default route, which is a gateway of last resort. So if it's not in my routing table, send it there. But we're not going to worry about it too much there. And if you see yes, you know, it checks the ARP table. And now why would it check the ARP table if it's directly connected? Well, because it's a neighbor in the LAN. If it's directly connected, it's in this network, right? So we check the LAN and blah, blah, blah. It looks for the MAC address of the device that it's sending to, sends it to it. If it's a remote network, it encapsulates the frame and forwards it out the exit interface to the next hop, right? So it puts its layer 2 information on there, forwards it. Now, if there's a gateway of last resort, encapsulates it, sends it there, same to the remote network. And if it has none of those, that means there's no route. So if a network doesn't have the route in the table and has no default route, it's going to throw that thing in the garbage. So if it only has these, it would stop here, right? If it's not in there, it's in the garbage. If it doesn't have any static routes, if it's not directly connected, just throws it in the garbage. And these are where most of your problems are going to happen. Probably the best show command is show IP route, right? Just show an IP route at privileged exec mode. And so we say show IP route. Show. Okay, now I'm doing show. Anyways, IP route. Just show IP route. Sorry, ROUT. There, that is a space in between it. Anyways, best command. Hit that one first if you're ever having a routing problem, and look for the network you're trying to send to, because that is where your problem is going to be 9 out of 10 times, that we don't have a network in there. Alright, so now what if we have multiple routes? Well, we got to determine best paths. Now, what I mean by multiple routes is, if you can see here, and we're sending to PC2, there's two ways. We can take here, or we can take here, right? So which one's better? Well, actually, this T1 is 56K is 56K, where T1 is 1.54 meg, so it's a lot faster than the 56K. Anyways, so alright, there it goes. And so we wanted to take that route. So dynamic routing protocols choose best path through. Each one has its own, what we call, administrative distance, which I'm not going to go over yet because it's coming, right? And that picks which routing protocol to use, and it's picked by which one's the most trusted. So administrative distance is trust, so that's coming up. And then they pick the routing protocol says they use different metrics, what's called a metric. Each one has a metric, and it says, hey, well, I'm going to calculate this speed and this speed to find the best route without a loop. So a dynamic routing protocol is trying to find the best route and have redundant routes without forming a loop so that everything crashes. And so, as we can see, it's going to show you the same thing as what I just said here. Boom. Which way do we take? Do we take this way? Oh, well, this is based on hop count, so that was a bad choice. So RIP goes off a hop count. That's its metric. And then open shortest path goes off of bandwidth, basically just bandwidth. We're just going to say bandwidth. And then EIGRP does bandwidth, delay, load, and reliability. By default, it only does bandwidth and delay, and it actually has a fifth K value, which bandwidth, delay, load, reliability. There's a third K, but I cannot think of what it is right now. Anyways, we will study that when we study EIGRP, and you guys won't study that until ccna3. So I'll tell you about that then. So RIP is way better. RIP is a horrible old routing protocol based just on hops, and it can't, because one hop of 56K looks closer than 2 through T1, and T1's way faster, so these OSPF and EIGRP would have found them better. These dynamic routing protocols, static or whatever, could also load balance so that we don't overload just one link. We send half of it one direction, half the other, and usually it has to be the same cost for which way it's going. Like it's going to have the same metric. But EIGRP, as it says right here, supports unequal cost load balancing if you enable it. So now we have administrative distance. And administrative distance is trust. And so the lower your trust, the better. And as you can see, connected has the lowest trust, and it's 0. So that's why a directly connected route is going to be chose before any remote route, as you saw there. So then the most trusted remote route is a static. It has an administrative distance of 1. And so why a static? Well, because I'm a network administrator, and because I've taken this class because I'm network administrator and I'm CCNA certified, so I don't make mistakes. So if I plug it in there, its administrative distance by default is going to be 1 because I'm always right. I don't know if that's true or not, but that's what I believe. I don't believe I'm always right, but I believe that if you're going to put in a static route, you don't want to make a mistake because it's the most trusted. Then, if we summarize EIGRP routes, they're trusted. External BGP, which is the routing protocol that runs the internet, and then internal EIGRP, IGRP, which came before EIGRP, OSPF 110, ISIS 115, RIP 120, external EIGRP 170, and internal BGP 200. Take a look at this because you need to know the routes of C, which is connected. This is in the routing table. S, which is static. D, which is EIGRP sometimes, which is actually internal EIGRP. and then you need O, which is OSPF. Make sure you know OSPFs, EIGRP, static, connected, and RIP for this chapter of what their administrative distances is. And so what it's saying is the higher up this list you are, if there is a route, 2 routes to be chosen from, right here, like if we're picking this best path, and we're running multiple routing protocols, which one do we pick? Well, based on our administrative distance, that's the one we pick first. And so if we have a route to multiple networks through multiple routing protocols, the higher up, you're going to be the one selected and shown in the show IP route table. Okay. Alright. So we've talked about this already. We're going to go over it again, I guess. Directly connected routes, right here. They're learned through programming this IP address. Remote routes, we're talking about for this router. These are the remote routes over here, as it says. And so it knows, we'll say this is A, B, C. Those are all been we had to put an IP address into the interface and a subnet. So it knows all of those networks. What it doesn't know is what it's not directly connected to. So the route's on the other side of R2. So we have to put in a static route or a remote. We either use a static route, which is manually routing, or a dynamic route using a routing protocol. So we say, hey, if you're looking for this network, go to here. Or if you're looking for this network, go out this interface right here. And that's how we program those. Or they're just dynamically learned like DHCP if we use a routing protocol. So routing table sources, I've kind of talked about these. We have local routes. Right here what it's showing you. It shows EIGRP routes, connected routes, L routes. So it shows you how they're connected. If you look at the top, if you ever forget, there's a key at the top, but a lot of tests will ask you what type of route it is and omit this information. So you do a show IP route, it says D is EIGRP, L is local, C is connected, S is static, R is RIP, right? So on and so forth. And you can look through those. But so directly connected are the ones with the C's or the L's, and then remote are everything else. Static is S. So static we're setting, and as you can see right here, it shows us our most important LCSDO. So local, connected, static, dynamic, or EIGRP, and OSPF. Alright, so next we go to what is the routing table. When we show IP route, it shows us D, so it shows us what type of route it is. So this is an EIGRP. Then the next thing is the network, the destination network that routing protocol has learned, or that's static or that connected, right? So that's the destination network, and that's right here, right? So that first thing we're going to see right after is our routing protocol. Then this orange thing right here, 90, which is the administrative distance of EIGRP. So the first thing we see in the box is the administrative distance. So if this was static, it'd be a 1, and if it's connected, it'd be a 0. Then this next number is a metric. So I'm taking that one off, right? So the metrics of EIGRP are wonky and huge. Static route just puts in a metric of 1 by default, and connected, I believe, is just a 0. And then it's telling us how we got there. So sometimes it doesn't have all this information. This is what we call an ultimate route that you're seeing. So it actually has the IP address that you are going to. So it says to get to 10.1.24. So if we can see 10.1.24, we're in this router and we want to get here. And so how do we get there? We go to this next hop right here of 209.165.200.226. and then this is the exit interface. So this is serial S00. So we're going to forward it out of here. So we could actually, when we program these static, if we're programming statically, we take this route out and just say, hey, if you want to get to this network, program out of here. And when it's a point-to-point, that's kind of a common thing. That's a point-to-point network, right? Only can have 2 connections on it. Or we could do it the other way of saying, hey, to get to this network, just go to here. Or we could put the whole thing in, and it's going to work the best that way. Anyhow, it depends what we're doing. So that's what the routing table is showing. Be prepared to be sick with seeing that window. It's never going away. We're just going to keep seeing it. Alright, so directly connected interfaces. How do we get that route in there? How do we get a directly connected route in? All we do is say no shutdown and program an IP address, right? So it's going to show us very little, right? This doesn't have a next hop because it just says, hey, this is the network. So it's just directly connected. We see it, and it just has the G00 like I was talking about, which is the interface that the network is programmed on, right? And that's where it's going to forward packets out of. The router is going to forward packets out for 192.168.10.0 out of G00. Right? So that's what we're seeing in this. Here's some more directly connected samples, how to do it, right? So it shows you just programming in that. So if you did this, I suggest you guys try it. Just draw a router, put a switch in there, put a PC like we did before, then do the same thing on 2 interfaces, program them, give them the no shutdown, put these computers in the same network, and see if they can ping and talk to each other, because they should be able to, because as long as you're in that routing table, the router can route to it. IP version 6. So how do we, well, we went over how to do IP version 6, so it's just the same thing on these directly connected routes. Let me make sure they're shown the same. And they are. They're just connected. Tell you what interface, say directly connected. So that's a directly connected route. So now we're going to static routes. And this is where we're starting to get a remote route. So with a static route, what we're trying to accomplish is direct route tells us this network, everything in the black, this network, right? We've programmed all of those in. But if we wanted to get to the internet, actually we're not even going to talk to the internet yet, because, oh yes, we were going to talk about default static route. So if we want to get to these pink routes over here, these are the ones we don't know, right? Because they're connected to a different router. And so that's what we're programming in with a static route. We're not programming in what we already know. So we do a show IP route, and you're never going to type any of those in. So what I'm going to do is I'm going to look at my great documentation. This is why we need great documentation. And so to program a static route, we just say IP space route from global configuration, config T, right? And then we put the route, not the actual network. We don't put like .1. We put the actual network address. So 10.1.1.0.255 /24 255.255.0, and then we either put the next hop, right? So in this case, R1 would be that 2226, the next hop right there, or we put the exit interface of there, or we put them both in there. Now there's another thing called a default route that I've kind of talked about, and this is how we'd get to anything we don't know, and that's how we'd get to the internet. And so what we would do with the internet one is we do the same IP route, but instead of writing the network out, we just put 0, 0, 0, 0, space 0, dot 0, dot 0, dot 0. 4 zeros. Our subnet mask is zeros, and our IP address is zeros. And that's allowing us to go to any network. So it's saying, if you're not in my routing table, send it here. And then we would program that with the next hop of, actually not right there, right here, right? Because this is the last part of our network we know. We don't want to say, hey, to get out of our network, go to over here where we don't know. We gotta know. We only know 3 networks, so it has to be attached to one of those 3 networks. All routes have to be attached to a network we already know, because we can't say, hey, get out of our network by going to a network we don't know. Alright, and so if my drawings didn't make sense, don't worry, they're going to show you here, I'm sure, in these examples of static routing. Alright, so if you look here, they put in a default static route, and they actually just had it forward out S00, which is fine because this is point-to-point, but probably better practice would be to go to the next hop in case you're in a multi-axis network, like where a bunch of routers are plugged into a switch, simulate an ISP or something like that. Default networks show up, default routes show up as, well, they're not even showing them because they show you going into, is in the first one? Alright. Right here. They actually had it highlighted, I just didn't see. It's a static route, right? So we programmed it statically, so that's what the S means. But if it's a default route, it has an asterisk on it, or a little star on it in the routing table. See how all the other ones don't have the star, and it does? Well, and if we go and look at our normal static route, where we're just programming for these 2 networks over here, see, they're just an S, and so that's the difference. And what we did in them, right, IP route, the network address, the destination network we want to go to, right, the one we don't know is what we're putting in, then the subnet mask, and then the exit interface, right, so they did that with one. And on the second one they did the IP route, the destination, where we're going, so 11, which actually we're doing for R2, so over here, going to 11, and then they put in 209.165.200.125. So why did they do that? It's the next hop it's the last known hop it knows before getting to this network. So that's what we do. Even if we had a network up here, we'd still say go to there, right? Because even if we want to know this network up here. Alright. So static IP version 6 route examples. For a default static route, remember, : represents consecutive zeros in IP version 6, and then we just put the prefix in with the slash. So do a /0, and we can do it the same way as we did with our routes. Static routes are exact same IP, except we say IP version 6 route, and then put in the network address with the prefix, and then our next hop. And so there's a lot more typing than there is in an IP version 4, just because there's more characters typically in IP version 6 addresses. Make sure you look at this one. Make sure you look at IP version 6. This is always, there's going to be a lab coming up where you do this thing, and people always say they don't know how to do this. So we're looking at 4333. Make sure you look at 4333 and see how you program static IP version 6 routes. And then why don't you just make it in Packet Tracer, because why not? You're going to have to do it in the lab anyhow. Okay, so then with static, notice it takes really good documentation. And what we have to know, right, is where we're going. It's kind of hard because we have to look at documentation and say, hey, I'm in this router, and I want to know how I get to this router, and I get there by looking at where I'm going. And so there's a lot to look at. So the dynamic routes are going to learn stuff automatically. We're just going to program them then. And they send hellos, or they all work a little different, kind of the same. But basically I just say how the dynamic route works is I say, hey, I know this network in R1, I know this network in R1, I know this network in R2, and I do the same thing for R2. I say, hey, I know all of these networks, and they'll form an adjacency, and they share with each other without me having to program in each one to each router. And the reason this is nice is to say, static routes aren't bad if we only have 2 routers, but if we have 3 routers, they start becoming a pain. If we have 4 routers, they become a real pain. If we have 10 routers, a complete nightmare. And there's a lot of room for error. And so that's where static routes start sucking. And so we have IP version 4 routing protocols, right? So we have EIGRP, which is a Cisco proprietary, lowest trust in Cisco devices. Why? Because it's Cisco proprietary. actually, I take that back. They opened it up, but you cannot use all features without being a Cisco device. Then we have OSPF, Open Shortest Path First. Probably one of the most popular routing protocols. ISIS, kind of used with by ISPs where they don't want to use OSPF or something like that, and less common, not really covered in this as much as, say, you're going to really hit EIGRP and OSPF. RIP, I think we just go over it. I believe it's in this chapter that we go over RIP, and it's end of life, and yeah, it's not great. If you look down at the bottom here, the focus of the course is on EIGRP and OSPF. RIP will only be discussed for legacy reasons. The other routing protocols supported by the iOS beyond the scope of the ccna certification. They actually took ISIS out of CCNP as well, but it is very similar to OSPF. Okay, so our dynamic routing protocol examples. Well, any of those things we just saw. I've kind of talked about this already, but we either see them with a D. So here's your quiz. These two have a D. This one has an asterisk with an EX. That means that it is a default static route being fed in through the OSPF. Remember, the S had an asterisk, made it a static route. So what's going on with this D, with that is it's saying, hey, it's going out of EIGRP because it's a static autonomous system, right? Static route. So it's feeding an autonomous to, it'll say, hey, the internet is right here. It's still feeding the internet to right there, learning it through EIGRP, but the static route is really in router 2. So instead of having to build that static route, it goes there, but the rest is just simple networks learned through EIGRP. If this isn't making sense, don't worry, you don't have to study EIGRP for a while, and there's a whole nother chapter on this dynamic routing stuff. Alright, IP version 6 routing protocols, they have different names. Router NG for next generation, OSPF version 3, and this is the hardest one to remember, EIGRP for IP version 6. Just kidding, that's the easiest one to remember. Okay, so OSPF version 2 is the dynamic routing protocol that we will primarily be hitting in ccna2. We will do some RIP too. I don't think I'll make you do RIP NG. So IP version 6 routing example. So we do a show IP version 6 route, and what do we see? Oh, just similar stuff to our last routing table, except that they have IP version 6 network addresses rather than IP version 4. Alright, so that was a fairly long chapter. Key things I want you guys to remember is definitely go over AD, okay, and the AD costs of those main ones I talked about: RIP, EIGRP, static, connected, OSPF. Then I want you to make sure you understand what a metric is. We're going to study more on metrics, so you don't have to really go over it. Understand how the routing table works, and we're going to work on the routing table more and more. But this was just a brief summary before we go into deeper stuff. So if you have any questions, send me an email or post it on the forum. This is a big chapter. If you're completely confused, read it over again, and don't worry, we have a whole lot more on this whole routing thing.